So here we go. So this lab is on siphon drainage, fluid dynamics. Siphon drainage isn't as important or as big of a situation that we deal with in perfusion as it was when I was growing up in the profession, because siphon drainage has been replaced by vacuum-assisted venous drainage. In some circumstances, kinetic-assisted venous drainage. Vacuum-assisted venous drainage allows us to use what? Bigger cannulas or smaller cannulas? Smaller cannulas, smaller pipes, smaller tubing. What we saw in the lab today is that, okay, another question. What equation is it that we're working with the effective radius on tubing? Anybody know the answer? French name? Passuet's equation, right? Passuet's equation, where it talks about the radius has a logarithmic effect on flow through a vessel, or flow through a cannula, or flow through a piece of tubing. So as the radius decreases, flow through that tubing decreases. We saw that in the couple different tubing things that we used today. How and why does that apply to us even though we're using vacuum drainage? When we start to terminate bypass, we need to take a bite of our venous line. Until we take a bite of 50, 60, even 70% of our venous line, we're not going to have an impact on the flow through that tubing because there's still going to be enough flow. Kinetic assisted venous drainage is where you use an actual pump in the line, in the venous line. So as you would turn that pump up, it would increase the negative pressure on the venous line, and thus as RPMs on that pump go up, your assisting pump, your negative pressure goes up, flow increases down our venous line. The same thing happens with larger tubing, or the height gradient increases. So as radius increases, as the height gradient increases, negative pressure on that line also increases, which pulls more volume. That's what we saw, correct? Conversely, smaller lines, smaller cannulas, taking a bite of our venous line and decreasing the radius will then decrease the amount of fluid coming down our venous line. How does this apply to us as perfusionists? Number one, we need to know the dynamics of the cannulas we're using. It's published. To flow through a cannula based on the size, based on the radius, based on the length, based on even the configuration of the holes in a venous cannula has an impact on drainage through the cannula. I've gotten into discussions with surgeons at different times where I had a surgeon that wanted to give me two 22s to drain a big Nebraska farmer, and I finally had to take the literature to him and say, hey, under perfect scenario, perfect conditions, each one of these cannulas maximum drainage is 1.5 liters. That means the most I can drain is 3 liters. If I need to flow 7 liters on this patient, there's no way that I can flow what this guy needs for a cardiac index if I can only drain 3 liters. He's a huge Nebraska farmer, and you're giving me, like, say, 2 Burger King straws to try to drain this guy with. It doesn't work, and it's physics. And I go, oh, I don't want to hear about your new concepts and things like that. Well, it's not new, it's physics. It's been around since the beginning of time. I can't change the physical laws of these cannulas. Does that make sense? So that's what we investigated today. As our height gradient increased, so the larger height gradient, we saw a greater negative pressure and more flow through, right? Then we applied that to what happens if we're using siphon drainage and we get air in our line. Either there is air in the heart that creates what's it called, an airlock, right? A siphon will only work if we have continuous fluid in that conduit. Once it becomes airlocked, it stops flow down the line. In that case, we need to walk the air out of the line. It's called walking the air. How does that work? You have to, number one, have fluid at the inside, or in the heart, or in our case, the bucket that we're using. It has to be submerged in fluid. There has to be fluid to fill that. If there's not enough volume in the heart to fill that cannula, it won't work. If the bucket drains and is empty, it's not going to work. We have to have fluid. It has to be submerged. Then we have to walk the air out, meaning we have to keep the air up in the tubing until we create a long enough part of that siphon where when we put it down, it chases the air out. We simulated this using a plumber's loop, a simple loop in tubing where we could inject air, a bolus of air, and then depending on the different size of tubing we were using, you got to investigate the height gradient of each individual piece of tubing and how much that height gradient was needed to push through a certain bolus of air. Obviously, a very small height gradient is needed to push 10 cc's of air out. When you get to 60 cc's or 120 cc's, or an entire tubing length, the amount of volume of air in that, it takes a much greater height gradient. Walking the air out is not complicated. However, as a perfusionist, you can't go up there and grab the line in the cannula at the field, can you? So you need to talk the surgeon, the scrub tech, whoever it is, the PA, and teach them how to keep that air up until you can grab hold of the line where it's not sterile anymore, and then continue to walk the air back to your bucket. These concepts should make sense. There's nothing here in these concepts that is not intuitive. That's not how we normally would think about things, but it takes practice. When we get to our swine labs, we're not gonna have vacuum in there. So we're gonna continuously use siphon drainage. We're gonna need a little bit larger cannulas in the pigs because we're not gonna have vacuum assisted or kinetic assisted venous drainage. Siphon drainage is very easy to use. As we've added vacuum to our circuit, especially if you have kinetic assisted venous drainage, your circuit gets a lot more complex. In some ways, we've made our circuit much more complex using vacuum. Throughout the summer, we will do some catastrophe labs dealing with vacuum and the problems that vacuum can create, i.e. leaving something clamped, leaving your vacuum clamped and vacuum on high and opening something, the vacuum will pull air across membranes, pull air into our circuit, may actually deprime our entire circuit with vacuum. So it's made the whole system a lot more complex than the old traditional siphon drainage, but it's allowed us to use much smaller tubing, much smaller cannulas, put a lot smaller holes in the heart, and essentially minimize our circuit and the damage to the heart with cannulation because we no longer have to worry about airlocks and creating the perfect amount of drainage from a siphon perspective. It also has allowed us to run our heart and lung machine setup much higher. We used to have to run everything right down on the floor, so we created that largest height gradient between our reservoir and the patient. Well, now with vacuum, we can run those very similar. You don't need to be bending over and have everything on the floor, which has shortened our lines up. It's gotten our setup much closer to the field and things of that nature as well. Any questions about what we saw today or about fluid dynamics? We're gonna put fluid dynamics, and with our last lab, the pressure dynamics lab, we're gonna start to build these different components in the next couple weeks, put them together. We've already initiated, maintained, and terminated. We're gonna start to learn, grow, and understand these concepts more, and then we're gonna talk about shunting and where flow is actually going in our patient in the coming weeks, before we start to have things fail, and before we start to troubleshoot things that can go wrong during this time. That sound good? Good job today.